The destruction of a capital ship is usually a sequence of escalating failures, but for the Italian dreadnought Leonardo da Vinci, it was a single, instantaneous physics event. On the night of August 2nd, 1916, the battleship sat at anchor in the Mar Piccolo of Taranto. She was the apex of Italian naval engineering, a steel fortress designed to withstand artillery and torpedoes. But her most dangerous enemy was not waiting outside the harbor defenses. It was stored inside her own aft magazines. Shortly after 11 o'clock at night, flames and smoke vented from the structure around No. 5 turret. Within minutes, at about 11:10, the after magazines detonated, throwing a towering column of fire into the summer air. The hull did not just fracture, it was subjected to a violent release of kinetic energy that lifted the stern and shattered the watertight integrity of the after section. In deep water, a magazine detonation usually sends a ship to the bottom in minutes, leaving only debris and an oil slick. But the Mar Piccolo was a hydrographic trap. At her mooring, the water was shallow, on the order of a few dozen feet, and that single fact dictated the geometry of the disaster. As water rushed into the after compartments, the center of gravity shifted violently. The massive dreadnought began to roll. She did not sink straight down because there was nowhere to go. Instead, she rotated. The stability curve collapsed and the ship turned turtle, rolling past 90 degrees, past 120 degrees. In the minutes after the blast, the roll became irreversible, and within less than an hour, the pride of the Regia Marina lay capsized. The roll fell short of a neat 180 degrees. The ship was wider than the water was deep. The ship was wider than the water was deep. As she inverted, her funnels, masts, and superstructure smashed into the seabed while the hull was still rotating. The soft mud of Taranto absorbed the impact, driving the steel towers deep into the clay. The ship came to rest at about 165 degrees, effectively pinned to the bottom by her own top weight. She was not just a shipwreck, she was a steel island, her keel breaking the surface of the harbor, looking like the back of a leviathan stranded in the shallows. Inside the overturned hull, the catastrophe was absolute. Between 248 and 249 men were lost, including her captain. The immediate investigation focused on the cause. In the first shock of wartime Italy, suspicion fell on the enemy. Sabotage, a concealed device, an unseen hand inside the harbor. That story had political power. It aimed anger outward, away from the uncomfortable possibility of an internal failure. But the record never settles into a single clean verdict. Some accounts point to deliberate action, others to negligence, handling errors, or the dangerous unpredictability of ammunition and propellant charges in a hot, enclosed magazine. In the end, whether it was sabotage or an internal ignition chain that no one could conclusively trace, the result was the same. Either way, the ship's stored war energy turned inward. The morning light revealed a salvage engineer's nightmare. The Leonardo da Vinci was not merely sunk, she was structurally integrated into the harbor floor. The standard methods of naval salvage assume a ship is resting upright or on her side, accessible to cranes and pontoons. But here, the ship was upside down, and the inner basin left almost no clearance around her inverted bulk. She was ground hard into the mud, held down by 24,000 tons of steel and the suction of the clay. There was no easy way to slip buoyant bodies beneath her, no clean purchase for a conventional lift. The Italian Navy faced a stark paradox. To save the ship, they would have to lift her, but the physics of her resting position meant she left almost no room to work. She was a mountain of steel that had fallen on its face, and every conventional rule of recovery suggested she should be cut up for scrap where she lay. To move 24,000 tons of dead metal requires a force that simply did not exist in 1916. The standard salvage procedure for a capital ship involves the deployment of pontoons and floating cranes. These external engines of buoyancy are attached to the wreck with steel cables to provide the necessary upward vector. But the most powerful cranes in the Mediterranean at the time could lift perhaps 100 tons each. Even if the Italian Navy lashed every available barge and crane in Taranto to the hull, they would not shift the mass of a dreadnought. The disparity between the available mechanical force and the required lift was 2 orders of magnitude. The physical reality of the anchorage dictated that no external machine could save the ship. General Edgardo Ferrati of the Corps of Naval Constructors approached the wreckage with a different philosophy. But he did not work alone. Naval constructors and salvage teams on the scene, including engineers who would later be closely associated with the operation, turned his concept into an executable plan. He recognized that applying force from the outside was mathematically impossible. Instead of pulling the ship up, he proposed changing the density of the ship itself. His plan relied on the principle of pneumatic displacement. This concept treats the inverted hull not as a broken vessel, but as a potential pressure chamber. If engineers could seal openings, control leaks, and pump compressed air into selected compartments, the rising air would push the water down and out through available low points and discharge paths, turning flooded volume into buoyant void. In effect, the inverted hull becomes a crude submarine, air in, water out, buoyancy rising. Ferrati calculated that if enough water could be ejected from the internal voids, the ship would become lighter than the water around it and rise to the surface under its own power. It was a brilliant inversion of the problem. The water, originally the enemy that sank the ship, would be used as the working fluid to lift it. The hull would become a bubble of steel, rising through the water column on buoyancy alone, at least in theory. However, the calculation faced a hidden variable that often defeats salvage operations in harbor environments. This is the phenomenon of suction adhesion. When a massive object impacts a soft, clay-based seabed, it does not just rest on the surface. It drives into the sediment, displacing the mud which then settles back around the perimeter. This creates a seal. If one tries to lift the object, the water cannot rush in underneath to replace it. A vacuum forms between the hull and the clay, generating a downward force that can be significantly greater than the weight of the object itself. The Leonardo da Vinci was not merely heavy. She was glued to the floor of the Mar Piccolo. Ferrati understood the air had to beat two loads, the ship's own mass and the suction seal holding her to the clay. That meant more than neutral buoyancy. She would need a surplus measured in thousands of tons just to break free. The compressors would have to run day and night, driving pressure in the riveted hull to its limits. The engineering team faced a stark realization. The volume of the hull was fixed. There was only so much space inside to fill with air. Even if they displaced every drop of water from the available compartments, the math remained hostile. The weight of the 12-inch guns, the heavy turret barbettes, and the thick belt armor exceeded the maximum buoyancy the air could provide. The ship was too dense. The bubble would not float. The pneumatic plan was the only viable path, but it could not work unless the ship underwent a radical physical transformation. The engineers had the lifting medium, but they did not have a ship light enough to be lifted. The numbers left no margin. Even at maximum output, the compressors could not make her buoyant against gravity and the mud. They could not add more lift, so they had to subtract weight. This led to a process of surgical reduction that turned the salvage into a demolition site. The target list included the heavy superstructure, the masts, and the funnels, which were buried deep in the seabed. But the most significant mass came from the primary armament. The Leonardo da Vinci carried 13 12-inch naval guns, each housed in a massive armored turret. In a conventional salvage, these valuable weapons would be the first objects recovered to the surface. But Ferrati ordered the opposite. The turrets were acting as anchors, weighing the inverted hull down. The divers could not lift them up, so they chose to let them fall. Working inside the flooded barbettes, divers cut the securing bolts and the critical connections that held the turrets to the ship. Once freed, those massive armored masses could be separated from the wreck, relieving the inverted hull of some of its worst dead weight. But they were not simply thrown away and forgotten. Salvage crews developed ways to bring even these monsters back. Flotation bodies and ring-like tanks, fed with compressed air, were used to coax detached turrets toward the surface and tow them clear. It was grim, methodical triage, not a theatrical sacrifice. Stripping the wreck down to something that buoyancy could finally argue with. With the heavy armor gone, the engineers faced a new and subtle danger involving the principle of inverted stability. When a ship floats normally, its stability depends on the center of gravity being low enough to counter the rolling force. But the Leonardo da Vinci was upside down. In this orientation, she acted like a pendulum. The heavy weight of the remaining upper works, now hanging deep underwater, provided the ballast that kept the keel pointing straight up. By cutting away the turrets and superstructure to gain buoyancy, the salvage team was effectively removing the weight at the bottom of the pendulum. If they cut away too much, the center of gravity would rise too close to the surface. The ship would become unstable and could violently roll onto its side the moment it broke free from the bottom. The calculations had to be perfect. They needed to be light enough to float, but heavy enough at the bottom to stay upside down. While the exterior teams cut away the steel, the interior teams waged a war against leakage. The hull had to be transformed into a perfect pressure vessel. This required divers to enter the inverted compartments, navigating a world where the floor was the ceiling and the overhead was the deck. They sealed hundreds of portholes, ventilator shafts, and hatchways, often working in zero visibility within the silt-filled wreck. Every opening was a potential failure point for the pneumatic lift. They built airlocks and patchworks of timber and cement, fighting to contain the air that would drive the ship to the surface. Finally, the compressors began the heavy work. They pumped air into sealed compartments, steadily forcing water out and reclaiming volume as buoyant void. But air alone was not enough. The wreck had to be made lighter before it could be made buoyant. Over months, the salvage became a controlled dismantling. Structure, fittings, and heavy elements were removed until the ship's effective weight had been reduced by on the order of 6,000 tons. As the internal water level dropped and the hull's buoyancy climbed, the plates groaned under unfamiliar stress. Then, without the assistance of a single giant crane, the grip of the mud finally failed. The Leonardo da Vinci broke suction. A plume of bubbles erupted around the perimeter as the ship surged upward. She stopped with her keel glistening in the sun, floating on trapped air and relentless pumping. The operation was a success, but the result was a terrifying anomaly. The battleship was afloat, a capsized monster, a 500-foot steel island drifting in the harbor, keel high and helpless. The refloated battleship presented a navigational hazard unlike anything in the history of seamanship. While the Leonardo da Vinci was no longer pinned to the seabed, her inverted bulk still bit deep into the water. In mid-September 1919, over several tense days, salvage tugs took strain on the tow lines to begin the transit through Taranto's confined waters. This was not a standard tow. The ship was effectively a 45 million-pound bubble of compressed air. She was being kept afloat solely by the pressure trapped inside the hull, maintained by a complex network of hoses and compressors running on the support vessels alongside. This precarious state relied entirely on the engineering principle of structural continuity. In naval architecture, a hull is designed to withstand the external crushing force of the ocean. But here, the forces were reversed. The internal air pressure was pushing outward against the steel plates, trying to escape. Structural continuity implies that the skin of the ship must remain unbroken and uniform in its resistance. If a single rivet popped or a temporary patch failed during the movement, the continuity of the pressure vessel would be compromised. The air would vent, the buoyancy would vanish, and the ship would plunge back to the bottom in seconds. The salvage crew had to maintain a perfect seal across acres of damaged steel while the hull twisted and flexed in the harbor swell. The destination was the massive masonry dry dock at the Taranto Naval Base. However, a dry dock is a concrete canyon designed to accept the keel of a ship, providing a center line of blocks to support the spine of the vessel. The Leonardo da Vinci was arriving upside down. Her keel was in the air, and her contact point with the ground would be her deck. The deck of a battleship is not a flat surface. It is a chaotic landscape of turret rings, superstructure stumps, ventilator housings, and capstan gears. It creates a jagged, irregular profile that cannot sit on a standard flat floor without crushing the ship's own upper works. To solve this, the engineers built a negative imprint of the ship on the dry dock floor, the Timber City. For weeks, carpenters and shipwrights raised a forest of cribbing, shaped to the inverted deck. Voids for every protrusion, towers for every flat run. The precision required was absolute. If the timber supports were even a few inches off, the 24,000-ton hull would settle unevenly, snapping the ship's spine or collapsing the dock floor. The docking maneuver was a slow-motion collision between the steel bubble and the wooden trap. The tugs guided the inverted hull over the dock sill with inches to spare. Once the caisson gate was closed, the pumps began to drain the dry dock. This was the critical transition. As the water level fell, the ship ceased to be a floating air bubble and became a dead weight resting on the timber city. The hull settled onto the wooden blocks with a groan of settling timber that echoed through the basin. The water receded, revealing the full scale of the salvage for the first time. The Leonardo da Vinci sat high and dry, a mountain of barnacle-encrusted steel towering over the observers, completely upside down. It was the primary anchor proof of the operation's audacity. They had not just lifted the ship, they had parked a capsized dreadnought on land. The pressure skin had held. The ship was safe from the sea, but she remained a prisoner of her own orientation, a vessel that could not be repaired until the world was turned right side up. The dry dock allowed the engineers to repair the hull, but it could not solve the fundamental orientation problem. The Leonardo da Vinci was still upside down, and there was no mechanical force on Earth capable of picking up a 24,000-ton battleship and flipping it over in midair. The solution required a mechanism carved into the harbor itself. The engineers dredged a massive trench in the seabed, a pit on the order of 60 feet deep, a geometric necessity to give the wreck room to turn. By January 22, 1921, the trench and its approaches were ready. 2 days later, on January 24th, the salvage team towed the inverted hull into position over the dredged cut. The operation now relied on the principle of parbuckling. In salvage physics, parbuckling is the use of leverage and internal weight distribution to induce a controlled rotation. Instead of trying to haul the ship upright with brute external pull, the engineers intended to make the ship unstable in one chosen direction. They would use water as a counterweight, loading it into the tanks on one side of the vessel until gravity took over and forced the hull to roll. The plan was simple and dangerous: flood the double bottom and side compartments on one side with several thousand tons of seawater. The added ballast would shift the center of gravity off the center line and build the torque needed to force the wide hull to roll. As the pumps filled the starboard tanks, the ship began to list. The movement was initially slow, a creeping adjustment of steel against water. The engineers watched the inclinometers, waiting for the critical threshold where the righting moment would become self-sustaining. For hours, the pumps ran, adding ton after ton of seawater to the high side. The hull dipped lower, the starboard bilge submerged, and the tension on the stabilizing cables spiked. Then, the physics reached the tipping point. The center of gravity crossed the pivot line. The ship lurched. The rotation accelerated rapidly, breaking free of calculation and becoming a runaway roll. The massive hull rolled through the water, sweeping a 90-degree arc in seconds. The submerged superstructure swung through the 60-foot deep trench, clearing the harbor floor with only feet to spare. The displacement wave generated by the roll surged outward, rocking the tugs and observation boats. A massive geyser of mud and water erupted as the upper works broke the surface for the first time in 5 years. The ship continued to roll past the vertical, oscillating wildly before settling into a stable, upright position. The Leonardo da Vinci was floating on her own keel. She was stripped of her guns, covered in rust, and scarred by the explosion, but the geometry had been corrected. The inverted mountain was a ship once again. The resurrection of the Leonardo da Vinci concluded in a world that no longer required her firepower. When the ship finally floated upright in January of 1921, the Great War had been over for more than 2 years. The strategic imperative that had driven the initial stabilization, the desperate need for a capital ship to fight the Austrian Navy, had evaporated. The battleship was now a masterwork of salvage engineering, but as a military asset, she was a ghost. She sat in the harbor of Taranto, a hull without guns, her interiors gutted by the explosion and the years of submersion, waiting for a refit that would never come. The final enemy of the Leonardo da Vinci was not a mine or a saboteur, but a piece of paper, and the politics behind it. In 1922, the major naval powers signed the Washington Naval Treaty, an arms control agreement meant to choke off a new battleship race. For Italy, it triggered a harsh reckoning: budgets, tonnage ceilings, and a fleet that had to be justified line by line. The Leonardo da Vinci, newly righted but stripped and brutally expensive to rebuild, became a symbol in that debate. In a post-war economy, the logic of finance and treaty-era fleet politics began to outweigh the logic of engineering. The decision moved toward letting the wreck go. 2 years after the triumphant righting operation in 1923, The Leonardo da Vinci was struck from the rolls and sold for scrap. The ship that had been lifted by compressed air, dry docked upside down, and flipped by the sea itself did not return to service. Dismantling began, and over time the torches and breakers reduced the salvaged giant to plate, frame, and ingot. There was no ceremonial return, no final voyage, and no battle honors. The hull did not vanish overnight. It was dismantled piece by piece under the cold arithmetic of the post-war order. However, the legacy of the operation survived the destruction of the steel. The salvage of the Leonardo da Vinci remains one of the most sophisticated applications of physics in maritime history. Not brute lift, but a wreck treated as a pneumatic system, with water and air made to do the work that cranes could not. The methods developed in the mud of Taranto became a reference case, widely observed, widely discussed, and studied as a hard-earned lesson in what capsized steel can be made to do. The visual proof was unforgettable. An inverted dreadnought dry-docked on a timber city, calculation holding back catastrophe. The loss of the ship in 1916 was a failure of chemistry and security. The recovery of the ship in 1921 was a triumph of intellect. The Leonardo da Vinci never fought the enemy she was built to destroy, but in the records of naval salvage, she is not remembered as the ship that blew up. She is remembered as the ship that was turned into a submarine, a bubble, and a pendulum, and brought back by the sheer force of human ingenuity.